Log on, tune in, find out. Another good idea from Cambridge.
I will give a very little or very brief motivation and present the model I'm looking at. We will then be looking at approximate optimal design, but then the main thing we're interested in is going to be exact optimal designs. Now, in my presentation here, I will confine the discussion to pairs, partly because I only believe in pairs and not that much in larger choice sets. And we have also already seen this idea of full profiles. So we describe the alternatives in the pairs by a set of attributes or factors. Here we have 3. And typically, we would use all the attributes to characterize each of the alternatives. And if we look at the same level of an attribute here in a full profile paired comparison, they would have different levels. Now, one may believe in that or not. So if you imagine increasing the number of attributes, then evaluating such a pair or several of such pairs may become more difficult. And that is what is known as the information overload problem in the marketing literature. And we have heard from Jordan that there does not seem to be any real empirical evidence for that. But if we accept that for the moment, then how can we deal with that? So one suggestion has been to use the so-called partial profiles, which Peter already nicely introduced. And here in the partial profiles, we allow only a specific number of the attributes to have different levels in the pairs. Now here in my little example with 3 attributes, you see the first 2, there the pairs, the alternatives here and here have different levels for the first and third attribute, but for the second they have the same. Now that is at least hypothesized to make the task easier, and also what is sometimes done is that then even those constant attributes are not presented at all for evaluation. Now the number of attributes that are allowed to vary, that is something I'm going to refer to as a profile strength throughout my talk. Now what is the setting I'm going to consider? So we will have k attributes. They are qualitative factors with levels 1, 2, and so forth up to the maximum number of levels. Each attribute may have a different number of levels. Profiles, as denoted here by S and T, are just k tuples or combinations of the levels of the k factors, and we can describe pairs in terms of those profiles. Now, in order basically to formalize the partial profile setting, now we're going to fix initially the profile strengths, the number of attributes that are allowed to vary, and then we get this design space for our problem. So we look only at pairs of alternatives S and T, which have different levels for exactly S attributes, where S is our profile strength. Now coming to the model, now what we're going to consider is if we first look at a single alternative, at a single profile with those levels of the k factors. So what we're going to use initially is what is known in the marketing literature as the part-worth model. So basically, the overall utility of an alternative or a profile is equal to the sum of the utilities associated with its levels. So here I have an additional term mu, and that is only being introduced here. Basically what I'm doing is I'm parametrizing that model as in an ANOVA model without interactions and k factors using effects type coding. Now the responses then are actually, we assume that they are the differences in mean utility between the alternatives S and T in a pair plus some random error here. Now if you look at this equation, and it's also stated here, now this is a linear model, so that is not a choice model at all. Why am I going to consider it this year in the session on choice experiments? But there are 2 reasons for that. On the one hand, in this conjoint literature, this sort of model is used when the responses are ratings. And on the other hand, as for instance John mentioned before, if we use the multinomial logit model which Peter presented and make this assumption of 0 parameters, so these which leads to the utility neutral designs, then an optimal design in this model will be optimal in the conditional logit model and vice versa. So now we will be looking at exact designs of a given size n, so a specific number of pairs, and that can either be a sequence of pairs, or it can be given by a design matrix where each row would basically code the difference in attribute levels for a pair. And if we have such an exact design, the normalized information matrix in the corresponding linear model has just this familiar usual form. Alternatively, we can look at approximate designs, and these are just discrete probability measures on the design space of partial profiles I introduced at the beginning, and that has an information matrix I denote by m psi. And because we have seen that so many times here already, I did not bother to actually write down the usual definition for that. Now, what is the problem I'm going to look at here? So we will consider the problem of finding d-optimal designs for paired comparisons of partial profiles. And the approach I'm taking is I use some invariance considerations about which I'm not going to talk because of the time, to get some optimal approximate designs, and then by getting some insights from the optimal approximate designs, we come up with optimal exact designs. Now I need to introduce a bit of notation, and so remember we have k attributes, so if we pick a set of s of those, in total they are k choose s of those sets, and this number is what we denote as n. Every individual set of s of the k attributes in some enumeration will be denoted by little m, where little m goes, of course, from 1 to capital M. And now we basically associate with each of those set of s factors pairs which have only different levels for those particular s factors. So we define a set Gm that consists of pairs which have different levels exactly for the s factors in the corresponding set Fm. Now these sets, the Gm's, are mutually exclusive, so these joint sets, and they give, if we look at the unions, they give the whole design space, so we have a union of the design space. Now by using the invariance considerations I briefly mentioned, so we can actually show that there exists a d-optimal design which has a specific form involving those sets of pairs, and that is the form which looks rather complicated. But what is the idea about that? So we have those sets of pairs, and in total capital M. With each of those we associate a non-negative weight. All those weights add up to 1. And then for each of those sets, we uniformly spread out the corresponding weight, Wm, over all the pairs in that set. So that is the idea about that approximate design. Now the point is that for those designs, so we know there is one that is d-optimal, which has this form, we can work out the corresponding information matrix, and that turns out to be something quite nice. So it has a block diagonal structure, so there's a block for every attribute. Now the blocks here are known, so they are completely symmetric matrices depending on the number of levels of the factor. So I here is the identity matrix, that is a vector of 1s, and these are the dimensions. Now there's another bit. For each factor there's a constant ck psi, and the expression for that is rather complicated. But what is the constant ck psi? So for every fixed factor little k, then ck psi is the sum of the weights for all the pairs which are such that they have a different level for the particular factor k. Now, in general, now we know that there is an optimal design which has this information matrix, but in general finding those constants here is not a trivial problem. Now we have proved a theorem which says if those constants here have specific values, then actually the sort of design I presented before is an optimal approximate design. However, because it's only a sufficient condition, it does not cover all cases. And so now we look at a slightly more restricted setting where we can basically say something about all the cases. Now that means from this point on, I'm going to divide or assume that all the attributes I have can be divided into two groups. All the attributes in the first group have the same number of levels, and also all the attributes in the second group have the same number of levels. So there may, for instance, be 10 attributes, but 4 of them have 4 levels and 6 of them have 8 levels. So that would be two groups. Now, we denote the common number of levels by U1 for the first group, U2 for the second group, and that is the total number of parameters in our model. And now, actually, in order to be able to formulate some results, we need to characterize or distinguish the different sets of pairs still a bit more carefully. So what we introduce is the type of a set of pair. So you may remember those GM were sets of pairs which are such that they had different levels on S of the attributes. Now such a set is to be set of type N1 and 2 if every pair, the two alternatives differ on N1 factors from the first group and N2 from the second group where the total is S. Now if we do that, we can actually now prove the result which in this setting covers all situations. So that looks pretty daunting. So I'm not going to try to go into any details about that, but what is important about this result is that depending on how many factors in the two groups we have and how those numbers are related to the profile strengths, in total we need to distinguish here 5 cases. In all 5 cases there's a different optimal approximate design. Now the important thing is, however, that in each of the cases our designs use at most 2 different types of pairs. So that means here, for instance, in case A, so the number of attributes in the first group and also in the second group is greater than the profile strength. So we are using only pairs here which have different levels for S of the attributes in the first group, and similarly pairs which have different levels for S attributes in the second group. And that similarly applies to all the other ones. Now, having that result, now coming back to this information matrix of the types of designs I'm considering, now we know the C constant, and the only point of this slide here is to say, okay, now if we have this 2-group case, now the information matrix we saw before where the C's were unknown, now we can actually pin them down, we have values for them. So the information matrix of an optimal design is fully known. Now, what we now want to do is actually, or summary so far, so we have seen there exist optimal approximate designs where the support contains only 2 different types of pairs and the information matrices are known. Now we want basically to find exact designs which have the same information matrix, which are then necessarily also the optimal. Now, how do we go about that? And I can only give a flavor about what is going on here, because otherwise I would need much more time. Now, but as a sort of motivation, you see here, you know, information matrix, we have many zeros here. So we have these off-diagonal blocks of zeros. Now, if we want to basically define now an exact design, so I'm going to define the design in terms of the design, construct the design in terms of the design matrix X, and later on reverse the coding. So if I then look at the information matrix of such an exact design, so that involves X transpose X, and if I want many zeros in that, so I may use bits in the construction which give me many zeros or a lot of orthogonality. So for that reason, I'm going to consider weighing matrices, which have only 3 values, 0, plus or minus 1, and which are such that W, so that is the square matrix, we say with n rows and columns, and if you multiply it with its transpose, that gives a multiple of the identity matrix, where W is the so-called weight of the weighting matrix. You may also use Hadamard matrices, and in order to combine them, we use Kronecker products. Now, actually, if we want to do that, so we have to bear in mind that in our theoretical result there were 5 cases depending on the sizes of the groups and the profile strengths. So we cannot expect one construction to work for all of the cases. So will be different constructions for the cases. And also because the weighing and Hadamard matrices do not exist for all values of n and w, so sometimes there simply is no weighing matrix where we would like to use one. So that means that in those 5 cases of the theorem, if I want also to have d-optimal designs which require only few pairs, and I would like to use a weighing matrix for this, if there is not the required one, so I have to use a different construction which perhaps needs slightly more pairs, and that means that in total for each of the cases there is not a single construction. So I'm focusing here only on one for case C of my theorem, and that's the construction 1. The theorem tells me that I only have to use pairs which are such that they have different levels for S factors from the first group, or in this case all factors from the second group, and S minus K2 from the first group. So case C was the one where the size of the first group was greater than or equal to S, which in turn was greater than the size of the second group. Now, and because I said I can only give you a flavor, now you see how such a construction looks like. Now that what to note here is actually, so if you look at the final thing, the X, each row basically codes a pair. Now we have here the vertical line which distinguishes the first group of factors with U1 levels from the second group of factors with U2 levels, and then the horizontal line distinguishes pairs of that type from pairs of that type. Now every W is some weighing matrix. Every H and every L is a submatrix of a Hadamard matrix. The ones here, these are vectors consisting entirely of ones. And finally, x1 and x2, they are basically, say, x1 for U1 levels gives all pairs of the U1 levels for that factor I can look at. So basically, that is the paired comparison model for a single factor that is used to code all possible pairs of U1 levels, and similarly here. Now, and that is why this here is only really sketchy. Now, if you choose all the bits in here in the correct way, so having appropriate dimensions, checking the existence, then actually what you can show is if you look at the X transpose X matrix of that, then it has the same block diagonal structure as my optimal approximate design, and the alphas here depend on the weight of the weighing matrices, the dimensions, and so forth. So I want to choose the dimensions so that actually I can get here the same constants, the C constants, as for my optimal approximate design, and then that exact design represented here is going to be an optimal one. Okay, so the rest of the talk then is very quick, because now I'm just going to show you how messy things become, because that is only one construction, one case. So if you want to cover all the 5 cases, so we're going to look at about 20 constructions. So basically, you see here all the constructions are labeled first with a letter which refers to the case in the theorem for which this applies, and then construction 1 is usually the smallest design, going up to construction 4, which is usually the largest one. But whereas the bits for, say, A1 do not always exist, the bits for A4 do always. So we always find an optimal design by those methods. And here you can write down the numbers of pairs. Now, I talked a bit about that there are things to consider about the dimensions and the parameters of the weighing matrices, and so you can actually work out all the conditions that need to be satisfied for a particular construction. Now, how on earth is anyone going to use that? So no one will ever probably go through the pain of actually looking at that. But we have actually written a program which, for the different possible total numbers of factors in group 1 and 2 with different numbers of level and profile strengths, gives you what construction to be used and the corresponding values of the design parameters. And in addition, we also have actually then reversed the coding in the design matrix and actually given the pairs so that they can be readily used, just copy and paste, and you could run a design on my web page. Unfortunately, I wanted to show that, but the internet connection here in the room is not working, but you can check out the web page. And finally, I said, or I was in a sense very sloppy about the technical details given the time, but if you're interested in that, you can look at those two papers. I finally should perhaps just mention my conclusions. Again, the designs here, although derived in the linear model setting, are locally optimal. So if the beta vectors seem to be 0 for the multinomial logit model. So that means they are exactly optimal in the setting considered, for instance, that Street and Burgess use when deriving their designs. The general method of piecing all these bits together can be used to get even smaller designs with a nice block diagonal information matrix, but then you have to give up some efficiency. And finally, I've looked at the case of here 2 groups of factors. We also did the thing for 3 groups of factors, but things become much more complicated. For instance, in my theorem here, I had to distinguish 5 cases. For the 3-group case, you have 50 cases. And then if you were to construct, then I would exact designs that would explode further. Okay, thank you very much. I think we're well on time. Yeah. Any questions? Yes, Angela?
Sorry, what are you doing? You're minimizing the variance covariance matrix, or
D-optimal.
D-optimal, but the variance covariance matrix for what exactly? The betas?
Yes, for the betas, yes.
And the betas are, I mean, are they a contrast? Are they comparing? Are they effectively? Is it a?
Yeah, I mean they are effects coded, so they are effectively a contrast, right?
A contrast between this level and maybe the lowest level or something like that.
No, because it's effects coding. It's the contrast depending on what sort of identifiability condition you're using. So the contrast between the utility of a particular level and the average of the utilities for all the levels of that factor.
Okay.
So the other one would be this dummy coding, which for some reasons I think
that's
I would not
also
prefer.
a contrast, but that's usually a contrast with the lowest level.
Yeah.
Okay, thank you.
Yep.
So for the 2 groups you mentioned that I think you call it types of designs, or only 2 types of designs for the
Types of pairs, yes.
Yeah.
Yeah.
What happens to the 3 groups? Is there also a limited number of?
For 3 groups, you would then have 3. Usually, you would have at most 3 types of pairs, and yeah. So that would basically be it. Sometimes you can do with 2 types of pairs in the 3-group case, but it seems, in a way, at least as far as we have looked ahead, it seems to be a similar general pattern. Say, yes.
You first of all worked out approximate designs and got the information matrix, and then you were looking for exact designs with information matrices of a similar pattern.
No, which were exactly the same.
Exactly the same. But would other exact designs have been more optimal?
These are the theoretical optima you can get, so there is no question of. Yeah. Okay, so if there are no further questions, I would like to thank all the speakers here in our session again.